All right, we are starting chapter 3, which is probability. So this lesson, like I said, it's pretty simple. It's a lot of your basic concepts of probability that you already know, or I know when I was doing like ACT prep, we did a little bit of probability. But there is a little bit of different types of probability that you probably haven't seen before. So we're going to kind of look at those 3 different types. You've probably heard of like, or worked with theoretical, we call it classical probability, but there's some other types as well. So when weather forecasters say that there's a 90% chance, oh yeah, Saturday's supposed to be like kind of actually a nice day too.
I know.
Not like super warm, but like better than this.
So yeah.
Fingers crossed. High of 48, I'll take it at this point. When weather forecasters say that, or a physician says there's a 35% chance for successful surgery, they're stating the likelihood or the probability that a specific event will occur. In previous chapters, we've more been talking about like the descriptive branch of statistics, and we talked about in chapter 1 how there's like those 2 different branches of statistics. Now the inferential, using statistics to make predictions, including like probabilities, like the big foundation. So that's basically what chapter 3 focuses on, is all probability. And hopefully we really do maybe like a little bit more like activities and like experiments, like what's the likelihood of rolling, some when you roll 6-sided dice or like kind of stuff like that. We'll see. All right, here's some vocab to start out. So a probability experiment is just basically like you performing the actual experiment and you're obtaining like your data, your results. So as an example, if we were to try to figure out like, let's use that rolling the dice example like I just gave, like the probability of rolling a 3 on a 6-sided dice, the actual probability experiment would be rolling the dice, that action. An outcome, this word comes up a whole lot. An outcome is the result of a single trial in our probability experiment. So let's say we rolled our dice and let's say we got a 3. That would be an outcome. So the set, we're going to use it like set notation. You've used that before, like an Elge 2. 3 would be one of our outcomes. We rolled a 3. The sample space includes the set of all the possible outcomes in your experiment. So if we're talking about a 6-sided dice, the possible outcomes we could roll a 1. So it's the set. A 1, a 2, we could roll a 3, 4, 5, or a 6. There's more sided dice out there, but let's just say this is a 6-sided one. All of those possible outcomes, we would call that our sample space. Okay, an event, so this also comes up a lot, is a subset of your sample space. It's just like a smaller set of all the possible outcomes that consists of one or more outcomes. So like if I said, what's the event that the dice number we roll is even? That would include the set of the possible outcomes of 2, 4, or 6. And that's what we often study with probabilities. Like, what's the probability that this event will occur? That the dice will be even. Okay, and then how we like calculate that, we'll get to in a little bit. All right, there's your vocab. One common way to look at like your sample space and all your possible outcomes for different types of experiences using like a tree diagram, which you've probably seen before, and if not, pretty simple and easy to interpret. Here's an example of one. We have one spinner that just has 2 sections, A and B. My second spinner has 3 sections marked 1, 2, 3, and then my third spinner has 2 sections of green and pink. And the 3 spinners are spun, and we want to figure out all of our possible outcomes. So here's what that tree diagram showing you. Like your first spinner, your 2 possible outcomes would be spinning on A or B. And then from there, for the second spinner, for each of those possible outcomes, we have, well, it could spin to 1, 2, or 3, 1, 2, or 3. And on that third one, green versus pink, etc., etc., etc. So here's kind of how they're listing the outcome. Like you could have A, 1, and then green. Or you could have A, 1, and then pink. Okay? And a tree diagram is like one visual way to look at all of your possible outcomes. It's not the most convenient because sometimes there's a lot of different ways or possibilities. So we'll talk about like mathematically what you can do in those situations later on. But just kind of practicing some of the vocab here. Part A says how many outcomes are there? Bless you. So this right here, this set, this is like my sample space, is a set of all my possible outcomes. So counting those up, how many outcomes do we get? 12. Yes, I heard it very quietly. 12. Okay. So these are each example, like this is one outcome, that's another outcome, and then the set of all of them is another sample space. How many outcomes do not involve landing on green? 6, exactly half of them, right? Because for every possible outcome, it can be green or pink. So half of them would be not green. Okay, how many outcomes involve landing on B and an odd number? All right, so for B, I would just look here, odd number, 1 or 3. And then for each of those possibilities, there's 2 possible outcomes, so it'll be 4. Okay. Kind of fun. So tree diagram, really like classic way of figuring out the number of ways possible outcomes can occur. All right, so it's kind of another vocab, I guess. We're gonna kind of segue into calculating probability in a second here. But we talked about events. And then there's kind of like 2 types of events, a simple event and a compound event. So a simple event is an event that consists of just one single outcome. And the other thing I want to point out here is that with events, we often like notate them with uppercase italicized letters like A, B, and C. All right, so I'll kind of like do an example and you'll see it's just a little bit of like picky notation. But let's say I have a probability experiment and I'm going to toss a coin and then I'm going to roll a 6-sided dice. So here's my tree diagram. Here's my possible, I could get heads or I could get tails. And then from there, those are my possible outcomes for rolling a 6-sided dice. So the event, tossing heads and rolling a 3, would be a simple event because there's only one way we could do that. By tossing heads first and then rolling a 3, that H3 is kind of how they're listing their outcomes. So we could say event A will be the set of the outcome H3. And again, this one is a simple event because there's only one possible outcome to do that, to toss a head and roll 3. So in contrast, what if they asked you to find the event of tossing heads and then rolling an even number? Well, you're like, okay, so I could toss a head, but then if I roll an even number like 2, 4, or 6, there's more than one, so that's not a simple event, or we call that like a compound. So let's call that one event B, H2, H4, H6. This would not be a simple event because it consists of 3 possible outcomes. All right, so again, the A and B is just to notate like an event. So if you see those uppercase notations, that's what that's saying. A simple event, you only have one possible outcome. Okay, good so far? Like I said, if you like, in this first lesson, it's a lot of the probability that you probably have been taught before or seen. Honestly, because it's, you know what's the thing about probability and like statistics part of classes is they're always like the last chapters in a textbook, like they're like chapter 11 or chapter 12. So it feels like in math classes, you just never quite get there. Can you guys think of like, this is an honest question, like the last time you were ever taught like statistic anything, like mean, median, mode, or like probability, like middle school?
Mm-hmm.
Probably?
I feel like 7th grade math. I
Seventh
remember doing
grade math.
having to memorize mean, median.
Okay. Did you ever do like probability? Have you ever learned like any probability?
I think we've like done activities, you know, with dice, but
Okay. In math?
yeah.
Do you know what class? I'm just honestly curious.
Definitely did it on Excel.
I think
I
don't know.
Excel.
Well, I think they did it.
We use ISO. I didn't love it.
I don't know.
I like Alex over there. I like Alex. It's nice. You guys are like, spent my whole first 4 months of school on Alex. Okay. Yeah, I feel, and you know what stinks is it shows up a lot on standardized tests. Like it shows up a lot on the ACT.
Yeah.
It shows up a lot on like those kids as like Aspire and Forward testing. Statistics are all the time. And it's just like something we never get to. I'm trying to figure out where would be a good time to like do more of it. Okay, anyways. Let's try an example problem with a simple event. A bag has 5 balls labeled A, B, C, D, and E. One ball will be randomly picked and its letter will be recorded as the outcome. Give the sample space describing all the possible outcomes. All right, so that is the set of all possible outcomes. So we could get A, we could get B, C, D, E. That'd be my sample space. Vocab check. What would be the event of choosing letter B? It would just be the set of the outcome of choosing the ball that's labeled B. Not to get confused with like, you're like, well, you just told us that uppercase letters mean events. And they can, but that's all you really need to list for that. This is just the balls also happen to be labeled with uppercase italicized letters too. So that's a simple event, because obviously there's only one way that we can choose to be. Let's look at something that's not simple, or something we call like a compound event. So this type of box has 4 cards that are numbered 1, 2, 3, and 4. Deborah will toss a coin once and record the toss as heads or tails. Then she will randomly pick a card from the box and record the number chosen. All right, give a sample space describing all the possible outcomes. So let's start with all our possible. If she tosses heads first and then she draws a card, she could draw 1, she could draw 2, she could draw 3, or she could draw 4. There's all my possible with tossing heads first. I have a really funny coin tossing story that I want to tell you guys after this. Tails. Same thing. Okay, so that's my sample space. Set of all the possible outcomes. The event that the coin toss is heads. We have more than one possible outcomes for this. We could have heads with a card drawing 1, heads with a card drawing 2, 3, 4. So hence that would be not a simple event because there's more than one possible outcome, or a compound event is what they call an Alex. Okay, here's my funny coin tossing story. One of Grant's friends, I swear, is like actually addicted to gambling. It's probably not something to joke about, but he like loves to gamble. And we did this like have you guys ever seen like those like pedal
Bar
Yeah.
things. Yeah.
Anyways, we did this event where he paid for everything. And so he was like, all right, I'll make everybody a deal. And there was like 20 of us. He's like, I'll make everybody a deal. You can do a coin toss with me. And if I win, you have to pay me double. And if you win, you don't have to pay me. So Grant and I were like strategizing. I was like, one of us has to try it. Like worst case scenario, we have to pay for 3 people instead of 2. But like if one of us gets it, then we only have to pay half. So I went first and I won. So then I was like, oh my gosh, you have to try it now. Because if you lose, then we pay our normal 2-person. And if you win, we don't pay at all. And Grant won too. So we ended up not having to pay. But he came out like 50-50 with like a lot of people had to pay double. And then a lot of people like didn't have to pay anything. But it was just kind of funny. Probability is a 50-50 chance. It had to tail. And he came out pretty much even. But we had a nice free day. Yeah, he loves to. One time I was doing him in coin tosses and it was $20 a coin toss. And I was like, tails never fails. And I called tails 4 times in a row and I won. And then I stopped because I was like, nope, I'm up. Like, I don't want to gamble any more of my money away. And then later on, he talked me into doing it again and he won like half his money back. But, good stuff. Good probability. Should be like, let me count the likelihood of me winning this before I can bet some money on this. Anyways, gambling is fun in appropriate amounts. That's a life lesson for you. This is going up on YouTube, so that's great. Okay. Next thing, you probably heard about this, and I talked about this when I did like ACT prep with like my LT2 kids about just like some statistic stuff. So as I mentioned, like tree diagrams are nice visuals to look at, like the number of ways things can occur or all the possible outcomes. But sometimes when you have large numbers of ways things can occur, it gets pretty not very, I guess, practical is a good word, to write out all the possible outcomes. So there's something called the fundamental counting principle. And this will help us find not the probability, but the number of ways, just like the number of outcomes of two or more events that occur in a sequence. So like tossing a coin and then choosing a card, something like that. So basically all the fundamental counting principle is you take the number of ways your first event can occur, we'll say m number of ways, and the number of ways your second event can occur, we'll call it n, and you just multiply those, and that's a fundamental counting principle. You'll get out the number of possible ways that that sequence can happen. So if we go back to like this one, for example, how many number of ways? My first event was tossing a coin. There's two possible outcomes for tossing a coin, heads or tails. Okay, and then there's 4 different possible outcomes for drawing this card. So to figure out the total number of possible ways, we could do 2 times 4. You get 8. And you'll see here 1, 2, 3, 4, 5, 6, 7, 8. Yes, or 8 possible outcomes in my sample space. That's a fundamental counting principle. Used when there's a larger number of ways or many different ways of things occurring. And this can be, you can apply this rule if there's like 10 different things you're doing. Not just 2 ways. You could just keep multiplying on the number of ways. So let's try an example here. So you are purchasing a new car. Here are the possible manufacturers, the possible size, and color. How many different ways could you select? 1 manufacturer, 1 car size, and 1 color. So instead of drawing a tree diagram and being like, okay, I can start with these 3 different ones, but then for each of those 3 different ones, I have 2 different car sizes, and for those, I have 4 different colors. We can just use the fundamental counting principle and take our number of manufacturing ways, which is 3, times the number of sizes, number of ways, sizes, 2, times the number of ways of color, 4, and there's 24 different ways, 24 different cars. Have you guys heard of the fundamental counting principle? On the next page, I copy and pasted the tree diagram so you can like visually see this and why like multiplication makes sense. For every 3, there's 2, and then there's 4 branched off of there. So then obviously there's all your 24 different outcomes. Okay. Let's try one more with the fundamental counting principle. This one's kind of fun because they give you little different like case scenarios. So you have an access code for a car security system, and it consists of 4 digits. Each digit can be any number from 0 through 9. Here's a common misconception. How many digits are actually in between 0 and 9? There's actually 10. Counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's actually 10 possible digits in between 0 and 9. Just think about it. In a code, you could use a digit like 0, right? All right, so I'm just going to call this digit 1, digit 2, digit 3, digit 4. You don't really have to draw out the boxes, but it is kind of nice, like visualizing this. So how many access codes would be possible when, A, in this first case scenario, each digit can be used once, only once, and not repeated? All right, so let's talk about how many ways could occur for digit 1. Well, for my first digit here, I have 10 possible ones. Let's say I use the digit 0. So now for my second digit, I only have 9 possible digits left. Let's say I use 1. Then for the third digit, I'm down to 8 different options. Fourth digit, 7 different options. So fundamental counting principle, instead of drawing out those possible situations, you can just multiply those and you get 5,040 possible codes. Have you guys ever done an escape room and you just keep trying a bunch of different random codes until you get it? You'd be there for a while, but yeah, I've done that too. And then you find the clue and that makes sense. I'm kind of over escape rooms. They were fun for like the first couple, and now I think I'm over it. All right. What if each digit can be repeated? Well, I would just have 10 for each. Or you can think of it as like 10 to the 4th. What do you think? 10 times 10 times 10 times 10. My code could be 0, 0, 0, 0 if I wanted. So 10,000. Lot more options. Okay. Last one says you can repeat the digits, but your first digit cannot be a 0 or a 1. All right, so our first digit cannot be a 0 or 1. So all that does is it only gives us 8 options for this. Can't be a 0 or 1. But then I can repeat the first digit. And I can repeat all the other digits. So from there, it would just be 10. So 8,000. Yep. Okay. So that was all practicing calculating like the number of ways something can occur. Not necessarily like the likelihood or the probability. That's what we're going to get into next. So this, as I mentioned before, like the theoretical, or sometimes it's called classical. Alex, I'm pretty sure, uses the terminology theoretical. I think that's why I put that one first. Theoretical is probably the type of probability that you've seen before or practice like calculating in a math class. But there are 2 other types of probability, something called experimental and something called subjective, and we'll get to those eventually. But the theoretical or classical probability, it's used when each outcome in a sample space is equally likely to occur. So like flipping a coin, rolling a 6-sided dice. Every outcome has an equal chance of happening. So how we calculate the likelihood that some event E, here's kind of like the notation, the probability of event E, we often do a capital P and then in parentheses E, so that's kind of read as like the probability of event E. Okay. So to calculate this probability, and probability can be represented in a couple ways. Decimals, fractions, sometimes even percentages, like the ones that you see, like 90% chance of rain, like that's obviously percentages. Fractions are kind of more common in math. So you just take the number of possible outcomes of event E, and you divide it over your total number of outcomes. And that's what we've kind of been practicing finding, is like the total number of ways something can occur. Total number of outcomes in sample space. It's often like kind of shorthanded as like success over total. Number of ways we can roll an even 3 on a 6-sided dice divided by the total number of outcomes, 6 possible ones. So the probability of rolling even is 1/2. So the other thing I want you to put in your notes is obviously our probability has to be, if we're talking fractions or decimal, it has to be in between the numbers 0 and 1. And then if we're talking percentages, our probability is in between 0 and 100%. So what I kind of noticed as I was looking through like the Alex problems is sometimes they'll tell you like write your probability as a fraction, write your probability as a decimal. I feel like they don't use percentages a whole lot, but honestly, this is like more where you see it in real life is percentages. But okay, so let's maybe try a couple classical theoreticals, and then we'll call it a day. If you're not too familiar with like a deck of cards, because there's some questions that involve a deck of cards, I copy and pasted all basically like your possible outcomes for a standard deck of cards. So there's 4 suits: hearts, diamonds, spades, and clubs. Hearts and diamonds are red. Spade and clubs are black, but colored on the cards. And then they range from aces to 10. Ace can sometimes be low, sometimes it can be high. And then you have like your face cards, jack, king, and king. Is everybody familiar with the deck of cards? Do you guys know how to play euchre?
Yeah.
You do? You do too? Do you? I feel like that's something we have to learn.
We have to play it.
Do you guys know how to play cribbage?
Yeah, I did.
Yeah.
A long time ago.
I love playing cribbage. It's like kind of mathy, so I feel like we could play it. All right.
We should play 6-handed euchre.
Final exam. Everybody has to learn how to play euchre.
Yeah, it's so much fun.
6-handed euchre?
Euchre is so much fun.
Did you say 6-handed?
Yeah.
I've never played 6-handed. Ooh. Yeah, it's a good time. Are you familiar with cards? Do you play euchre? Well, okay. All right, guys, I'm impressed. I feel like when I went to college, nobody knew how to play euchre because it's like a Southwest Wisconsin thing.
I know how to play spoons.
Phase 10. I know it's not a deck of cards. That's like the funnest card game ever. I love Phase 10. I'm so
Get
fun.
mad over
I am so mad too.
Is that
Me too.
is that where wait, what's that?
There's like different phases, like you do 2 sets of 3 or run a 7.
And if you don't, like, you have to stay on a certain, but
Yeah.
everybody else gets to keep going
Yeah.
until you get the certain.
You can play it with a standard deck of cards. We did that in Florida with my
We put it
family.
online now.
I played a bunch of games before, so
It is fun.
card games now.
Okay, so anyways, there's 52 cards in a deck. Here's all the cards. So, and I know on Alex too, I think it says like, if you need a reference, a card sheet or whatever, you can like pull it up on there. But what would be the probability that the card drawn is a black colored card? So, obviously you guys probably know that half of the deck is colored black here, but if we were to think about how many total possible cards, if you were to count these up, there's actually 26. And I'm going to write it this way just because we're kind of practicing. So that's my event that the card would be black. There's 26 ways that could happen. All of these ones. So. That's how you calculate probability. Total number of success ways, so 26 out of total number of cards, 52, which reduces to 1/2. I stole this column from Alex, and they kept the answer as 26 over 52, which I don't know why, because almost always in probability we reduce it, and with any fraction, so you have to play around with it. I'm sure it'll count both correct, but it might like say like, oh, don't simplify your answer, or oh, simplify your answer, so you have to play around with it. Okay. What would be the probability that the card drawn is an ace? So how many aces are in a deck of cards? 4, yep. Over my total, 52, which would be 113 as a simplified fraction. Okay, this next one's interesting. What's the probability that the card drawn is a black card? So it's either a spade or a club suit, or it's an ace. Okay, so we have 26. If we count up all these, 26. And then what other ones do I have to include? The aces, yep. So some people might think 30 over 52, but then you're double counting these. Okay, so And again, you can use this to count, reference a number of ways. It'd be these 26 plus those 28 possible ways out of my total, 52. So 7 over 13 is that fraction reduced. Alright, I feel like it's probably a good starting point. Yes, thank you for waiting. So patient.
Just bring it at you. I am no.
Yeah. Is that for Wednesday?
I just keep rewatching.